one and all. Myself Sreevani, working as an assistant professor in the Department of ECE in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So in the today's lecture, we are going to learn the one of the topic or important topic in magnetostatic fields as forces due to magnetic fields. So there are three cases in this exist, that is forces due to magnetic fields. So out of that, we are going to learn there are at least three ways in which forces due to magnetic fields can exist or can be experienced. So, in order to learn magnetic forces, there are three cases. The first means the force can be is of due to a moving charged particle in a B field. B field is said to be magnetic field. B is the notation for magnetic flux density, and instead of considering B or H is similar analogy. So the first classification or the first case which we have considered for the magnetic field force can be due to moving charged particle in a B field or magnetic field. And the second case is on a current element in an external B field, external magnetic field. The third case is it is between two current elements. Means the forces due to magnetic fields can be experienced in three different cases. One is it is due to a moving charged particle in a magnetic field, and second case is on a current element in an external B field, or it is between two current elements. So individually we are going to estimate or we are going to calculate the or derive the equations for a moving charged particle in a magnetic fields and on a current element in an external magnetic field, or it is between the two current elements. So the first case which we are going to learn is a force on a charged particle. First case. Force is given by the notation as F on a charged particle. Means generally the static object which is denoted with stationary charge as Q. So in order to derive the condition or the equation for this force on a charged particle, we have considered two electric fields analogy and magnetic field analogy. That is, the electric force means generally the notation for force is F and it is related with electric fields, hence the notation is Fe. Means the electric force Fe on a stationary or moving electric charge. We know that electric charge is generally represented with Q, and it is if it is a fixed one or it is moving with a velocity, then depending upon that the electric force Fe on a stationary or moving electric charge Q in an electric field is given by Coulomb's experimental law. By default, we know that according to Coulomb's law, means it gives the relation for electric force. Then from that Coulomb's experimental law, and it is related to the electric field intensity E is given by Fe equal to Q into E. How it is obtained means we know that electric field intensity E is given by, according to its fundamental definition, E equal to force per unit charge Q, and it is placed in a field called electric field. And here the electric field intensity E is measured in volts per meter, and force can be expressed as newtons, and charge Q can be measured in the coulombs. So there are two different units for this electric field intensity. Sometimes we used to consider as Newton per coulomb, or sometimes it might be with volts per meter. So Fe equal to Q into E. So from the definition of electric field intensity, E equal to F by Q, and from this we have got the relation F equal to E into Q. Hence Fe equal to Q into E. So that is to be obtained as the electric force Fe on a stationary or a moving electric charge Q in an electric field is given by Coulomb's experimental law, and it is given by the relation, or mathematically we can express it as Fe equal to Q into E. And this shows that if Q is positive, Fe and E have the same direction. If Q is negative, two are moving in opposite directions. So there are three different notations for charges, as sometimes we used to consider it with capital Q, or sometimes we used to consider it with small q, or sometimes it might be with E. Three are the same notations for the charges only, that is electric charge only. So this is the equation which shows that, means if Q is positive, electric force Fe and electric field intensity E are in the same direction. Next, so from this equation we have got electric force equation. Now, so from the next means the magnetic field can exert force only on a moving charge. Why? Because electric fields, or how the electric field is generated, means due to the stationary charge or fixed charge as Q. If the same charge Q or stationary charge Q is moving with a velocity as U, then the field is said to be magnetic field. Hence, a magnetic field can exert force only on a moving charge. Moving charge means this charge is denoted with Q and it is moving with a velocity of an electron, hence it is Q is denoted. Then from the experiments, it is found that the magnetic force Fm. So as we have considered for the electric force as Fe and magnetic force means Fm. So M is the notation for magnetic fields, F is the notation for force. And experienced by a charge Q moving with a velocity U in a magnetic field B is given by Fm equal to Q into U in the field called magnetic field, and it is denoted with B, where B is magnetic flux density. So where Fm equal to Qu into B, where this is not directly considered as multiplication, but it is curl of magnetic field B. So curl means rotational way we have considered different vectors. So electric force is given by Fe equal to Q into E, and the magnetic force is given by Fm equal to Qu into B. So this shows that Fm is perpendicular to both U and B. Why? Because Fm, U and B are exactly orthogonal to each other. So the angle between U and B, or B and F and U will be exactly 90 degrees. Hence, Fm and B are perpendicular to each other. So from these two relations, we have got electric force as Fe equal to Qe and magnetic force as Fm equal to Qu into B. Next, so Fm cannot perform work because it is at right angles to the direction of movement or motion of the charge. In general, we have considered it as Fm dot dl is equal to 0. Then that is to be obtained means the magnetic force Fm is generally small compared to the electric force Fe, except at high velocities. At high velocities, 2 are means Fm is small when compared to the Fe, where Fm is magnetic force and Fe be the electric force. So for moving a charge Q in the presence of both electric as well as magnetic fields, in the presence of electric fields as well as magnetic fields H, then the total force on the charge, and it is given by, means the total force due to electric as well as magnetic forces can be given by here F equal to Fe plus Fm. And we know that Fe is given by Q into U, E, and that is from E equal to F by Q. Force per unit charge is given by electric field intensity, then from that F equal to Eq, and it is considered for the electric force. Similar consideration for magnetic force means Q into U cross B. So this is the 1 and here it is the 2. Then F total force related to electric as well as magnetic fields can be given by F equal to Fe plus Fm. Right? Now if you substitute Fe by Q into E plus Fm by Q into U cross B, then if you take here in these two terms Q as the common, then E plus U cross B is the resultant one. So F is given by F equal to Q into E plus U cross B. So that is the equation which we have got here, F equal to Q into E plus U cross B. So this is the equation which is called as Lorentz force equation. So to derive this Lorentz force equation, we must consider electric force along with the magnetic force. So equation is obtained as F equal to Q into E plus U cross B, where F is the total force which is related to electric as well as magnetic fields, and Q be the charge of an electron, and E be the applied electric field, and U is velocity of an electric field, velocity of an electron, and B be the applied magnetic field. So due to electric as well as magnetic fields, hence the combination of that resultant force equation is said to be Lorentz force equation. So derive the condition for Lorentz force equation means we have to obtain the total equation as F equal to Q into E plus U cross B by considering electric forces along with the magnetic forces. So this is related to force on a charged particle. Means the condition to be obtained for the force on a charged particle means we have to consider electric force as well as magnetic force. By combining two forces will be the total force related to the both magnetic as well as electric fields. Then resultant force equation is said to be your Lorentz force equation. That is F equal to Q into E plus U cross B. Then the mass of the charged particle, if you consider it as M, and it is moving in electric as well as magnetic fields by M by the Newton's second law. As we know that according to Newton's second law, that is the equation given by F equal to M into A. Then if you substitute in place of A by a change of velocity with time, then F equal to M into A is the acceleration, and it is given by A equal to du by dt. Then if we substitute A by du by dt in this equation, then M into du by dt, which is equal to then force related to electric as well as magnetic fields from the Lorentz force equation is given by Q into E plus U cross B. Then the solution to this equation is important to determining the motion of charged particles in electric as well as magnetic fields. So we should bear in mind that such fields energy transfer can be only by means of the electric fields. Why? Because if you compare, the electric force is more than that of the magnetic force. Right? So F equal to M into A according to the Newton's second law, and it is given by from the Lorentz force equation Q into E plus U cross B is the total force related to electric as well as the magnetic fields. Next, second condition means the force experienced on a current element. So first we have discussed the first case as force experienced on a charged particle. Now the second case which we are going to analyze is force experienced on a current element. So by default we know that current elements means the three continuous current elements in the magnetic fields as IDL and KDS and JDV are the three current elements. So IDL is for line and KDS is the for surface and JDV is for the volume. So remind or keep in mind this, the relation between three current elements in the magnetic fields are given by IDL equal to KDS equal to JDV. So to determine the force on a current element, hence current element that is related to IDL, first one, of a current carrying conductor, only one line direction. Hence we have considered the line current element as IDL. So to determine the force on a current element IDL of a current carrying conductor due to the magnetic field B, hence is given by first J equal to rho V into U. So this is the equation which we have got it from the convection current density. This already we have learnt in the case of electrostatic fields. Convection current density. and it is J. Current density is denoted with J and rho V into U, where rho V be the volume charge density and U is the velocity of an electron. So according to the convection current density, that current density is given by J equal to rho V into U. Now consider that as equation number 1. Now by recall the relation between all three current elements, just now we have recalled, that is IDL equal to KDS is equal to JdV. Line current element, surface current element, volume current element. So if we combine, means consider this as another equation, let it be equation number 2. So from the one, means from the convection current density, J relation is J equal to rho V into U, and by recollecting the relationship between three current elements as IDL equal to KDS equal to JdV. Now if we combine these two, means combining equations 1 and 2 yields. So resultant will be, means consider first one of the relation as ideal equal to, and first and third relations. If we consider ideal equal to JdV. So by combining those two, ideal equal to J into dV. If we consider first relation as ideal equal to J dV. And we know that J is given by according to convection current density rho V into U. Now substitute in place of J by rho V into U into dV. Then if we separate this one as U separately, rho V into dV. So in electrostatic fields we have three continuous charge distributions, means rho L into dl is nothing but rho S into ds is nothing but rho V into dV, where rho L, rho S, rho V respectively called as line charge density, surface charge density and volume charge density. So these are all the relations for charges, right? So Q is nothing but rho L dl, nothing but rho S into ds, and it is nothing but rho V into dV. Now if we replace this one rho V into dV by Q, then our rho V means dq, differential elements. Hence dq is nothing but rho L into dl, rho S into ds, rho V into dV. Or if you want to find q value, then we are going to apply both sides integrations. Then it becomes integral L rho L dl, integral S rho S ds, integral V rho V dV. So differential elements means here dq equal to rho L into dl, nothing but rho S into ds, nothing but rho V into dV. Now if we substitute rho V into dV by dq in this equation, then dq into u as the relation we have got for the IDL. So consider here first and three relations as IDL equal to JdV. Then if we substitute J by convection current density value as rho V into U, then IDL equal to rho V into U into dV, which is nothing but where rho V and dV is replaced by dq into U. Or this is the way we can relate IDL is equal to dq into U as one relation, and another one is if we consider IDL means the current IDL if we consider as the line current element, which is nothing but means in general we can define the current I is nothing but charge per unit time. Current can be defined as charge per unit time, means Q by T. So for the differential element means this is given by dq by dt, hence it is dq by dt. So if we replace IDL means IDL by here dq by dt into dl, or which is nothing but dq into dl by dt. Change in the displacement to the time is given by its velocity. Hence, dl by dt is given by u into dq. So this is the way also we have got one of the relation between ideal for the dq into u as ideal equal to dq into u, or according to if you use convection current density as J equal to rho V into U, if we substitute, then that is the relation also ideal equal to dq into U we have got. So alternatively means either of the methods we are going to use. Hence, ideal equal to dq into U. This is from the fundamental definition of the current, and this is from the convection current density. So hence ideal is equal to dq into u. In both the methods, we have got the relation for ideal in terms of charges and velocities are given by ideal equal to dq into u and ideal equal to dq into u. So consider that as the relation. Now, the force on a current element ideal in a magnetic field B is found from the merely replacing QU by ideal. Hence, dF equal to ideal into B. So, force can be given by here in the previous magnetic force can be given by QU into B. So where this is, if you consider DFM, differentiation on both sides, then this is the equation which we have got here, DFM equal to DQ into U into B. So DQ into U is nothing but IDL into B. So this we have got it from the previous analysis, that is IDL equal to DQ into U. So if we replace here dq into u by ideal, then the df is obtained as ideal into b. So consider this as another equation, let it be equation number 4. If the current I is the current I is through any closed path L of a circuit, then the force on the circuit is given by. Means if that circuit to be a closed one, hence we have considered F is equal to integral, means now to get, so dF is nothing but here differentiation of the force element. Then from that, if you want to get F, then consider both sides integration. Then F is nothing but dFm equal to ideal into B. Then from this, if you want to get Fm, consider both sides integration. Hence, it becomes Fm equal to integral L ideal into B. Right? So, closed line integral hence. Right? So, F equal to closed line integral L ideal into B, and this is equation number 5. Now, if instead of the line current ideal, so till now we have considered current element means the line current, hence ideal. Suppose instead of having this line current, if you have surface current or if you have volume currents, then we just replace ideal by KDS for surface current and JDV is for volume currents. So if instead of the line current ideal, then we have surface current elements KDS or a volume current element as JDV. Then dF is given by KDS into B, or for the integration, that is F is equal to closed surface integral S KDS into B, or dF for the volume, dF is nothing but JDV into B, or F is nothing but integral V JDV into B. So the magnetic field is defined as the force per unit current element. Hence, F is to be obtained in the case of line as closed line integral L ideal into B, for the surface closed surface integral S KDS into B, or for the volume integral V JDV into B. Right? So from this relation means the force experienced on a current element, means we need to recall the relation between three current elements as ideal equal to KDS equal to JDV. Then from this we have got the relation as ideal is equal to dq into u. Then according to magnetic force, Fm is equal to dq into magnetic force q into u cross v. Then if you find both sides differentiation, then dfm is equal to dq into u cross v. Then if you substitute dq into u by ideal, then into b is dfm. Or from this, fm means integral L, closed line integral L ideal into b is for line, and fm equal to for the closed surface integral S KDS into B, and for the volume it is Fm equal to integral V J dV into B. Right? So this is the way we can get the three current elements relations, or the force experienced on a current element is whether it is related to line current or surface current or volume current. then the three relations are to be obtained as Fm equal to integral L ideal into B and Fm equal to integral S kds into B, Fm equal to integral B jdV into B. All the cases it must be closed, right? So integral elements means these are the three integral elements. Or from this we have got ideal into B means kds into B or sometimes jdV into B. So this is not the into one. Then we know that the relation between F and B is mutually perpendicular or orthogonal to each other. So this is the way the force experienced on a current element is given by or it is defined. The force per unit current element is to be obtained. Next, the third relation is force between two current elements. The force which is experienced on between the two current elements. So for the first current element, only one current element means we have considered the relation as IDL. Between two current elements means two different currents we need to consider along with the directions are also two. So I1 DL1 as the one, next one is I2 DL2 as the another one. So first one as 1, if we consider two concentric circles with the 1 and 2 conductors, and if we have the first conductor which is having the current element as I1 DL1 and with the second one it is to I2 DL2, and if you want to find the distance from 1 to 2 then it is from the R21 if you observe this is the direction, or if you want to find the distance from 1 to 2 we are going to consider it as R12. Either of the directions we are going to consider R12 or else R21. R12 is from 2 to 1 and R21 is from 1 to 2. And here is the component D of dF1 means differentiation of the force which is related to the first conductor. Or D of dF2 means differentiation of the force which is experienced on the second. So let us consider now the force between two current elements means for the first current element as I1 DL1 and for the second current element as I2 DL2. According to the Biot-Savart's law, as we know that Biot-Savart's law means it gives the relation for the magnetic field intensity and differential component of magnetic field intensity is directly proportional to the current element IDL and the sinusoidal angle between the current element to the point P where we are going to estimate the magnetic field intensity. Or DH is directly proportional to IDL into sin alpha and it is inversely proportional to the square of the distance between the current element IDL and the point P where we are going to calculate the magnetic field intensity. So differential component of magnetic field intensity DH is directly proportional to the IDL into sin alpha by r square. If we replace the proportionality constant with the constant k, then DH is equal to k into IDL sin alpha by r square. Or if you replace this k by 1 by 4 pi means its constant is given by 1 by 4 pi, then DH is equal to IDL into sin alpha by 4 pi r square. Okay, then here the magnetic field intensity H is always a vector. Hence, in order to express that one in terms of vector, we just replace the sin alpha by vector form. Hence, it is IDL into AR by 4 pi r square, where AR is the unit vector to that respective direction. So, this is the Biot-Savart's law, DH. So, according to Biot-Savart's law, both current elements produce magnetic fields. Hence, DH is equal to IDL, DH is equal to KDS or DH is equal to JDV. Hence, according to the Biot-Savart's law, both the current elements as I1 DL1 and I2 DL2 both can produce magnetic fields. Then we may find the force means D of dF1, differentiation of force 1 on the first current element as I1 DL1 due to the field dB2. Suppose if you want to find d of df2, if you want to find d of df2, then this is given by the force on F2 means on I2 dl2 due to the field called magnetic field called V1. So produced by the current element I2 dl2. Hence, that is the equation is given by d of df1 means previously we have got df1 is equal to idl into b. So if you want to find the first one df1, then I1 dl1 into that is due to b2. So again if you want to apply differentiation, then d of df1 equal to I1 dl1 into db2. Right? In place of this dB2, so we know that the relation between B and H is B equal to mu naught into H. Then from this, if you want to substitute B2 by H, means this differentiation component dB is equal to mu naught into dH. So from the Biot-Savart's law, the relation is given by IDL into AR by 4 pi R square. So from that, d of df1 is equal to I1 dl1 into dv2. Suppose if you want to write the equation for d of df2, which is equal to, so it is related to the second current element means I2 dl2 with a field, first field as V1, hence it is denoted with db1. There is a difference, that is d of df1 is for first current element I1 dl1, the field produced by that is V2. Now, in order to calculate this d of df2 related to the force second element, that is I2 dl2 into the field which is produced by the first current element as db1. Right? So, this is the way we have considered d of df1 or differentiation of second current element. So, from the Biot-Savart's law, we know that we have got first relation dH is equal to IDL into AR by 4 pi R square. This is from the Biot-Savart's law. This is from the Biot-Savart's law. So, dH is equal to IDL into AR by 4 pi R square. Now, from this, if you want to find dB, then mu naught into IDL into AR by 4 pi R square. Why? Because we know that V and H relation is V equal to mu naught into H. Hence, dB2 equal to mu naught I2 dL2. Why? Because we are writing the equation with respect to the field 2. Hence, dB2 equal to mu naught into I2 dL2 into AR21 by 4 pi R21 whole square. So, it is related to the second current element. Hence, I2 dL2 is the second current element and the direction we are calculating from 1 to 2. Hence, it is AR21 by 4 pi R21 square. So, in general, we have here AR by R. Now, AR21 to the R21. So, dB2 equal to mu naught I2 dL2 into AR21 by 4 pi R21 square. Right? So, d of df1 equal to, in the previous equation, we have d of df1 is equal to I1 dl1 into db2. So, in place of this db2, if you substitute mu naught I2 dl2 into AR21 by 4 pi R21 square, then first current element as I1 dl1, hence I1 dl1, and the db2 is given by mu naught I2 dl2 into AR21 by 4 pi R21 square. So, d of df1 means differentiation of the force 1 due to the first current element as I1 dl1 is to be obtained. Based upon that, the field produced is related to the second field. Hence, dB2 is to be considered as I1 dl1 into mu naught I2 dl2 into AR21 by 4 pi R21 square. Right? So, 2 times differentiation of F1 is given by this one. So, I want to find the value of F1. So, to find the value of this F1, we have to apply 2 times integration now to cancel these two differentiation elements. Hence, First, if you apply one-time integration, then df1 is to be obtained as integral L2 I1 dl1 into mu naught I2 dl2 into AR21 by 4 pi R21 square as the first. Then again, if you want to find F1, again we need to apply integration, hence double integral L1 L2 mu naught I1 dl1 into I2 dl2 by 4 pi R21 square into AR21 or 21, right? So F1 equal to, if you consider mu naught I1 I2 are the constants and 4 pi is also to be considered as a constant, hence mu naught I1 I2 by 4 pi close line integral L1 L2 dl1 into dl2 into AR21 by R21 square, right? So dl1 is for the differentiation of first line current element and the second line element, and with the direction as AR21 by R21 square. So the force F2 and the loop 2 due to the magnetic field B1 from the loop 1 is obtained from the same equation by interchanging the subscripts 1 and 2. So it can be shown that F2 equal to minus F1, which is similar analogy for the Coulomb's law. So thus F1 and F2 obeys Newton's third law, that is action and reaction are equal and the opposite. So in a similar way, we are going to calculate the equation for F2. So to calculate F2, we have to consider d of dF2, which is nothing but I2 dL2 into dB1. So dH is, we know that ideal into AR by 4 pi R square according to Biot-Savart's law. Then if we substitute B by mu into H, then mu naught ideal into AR by 4 pi R square. Then which is equal to, so I2 dL2 into mu naught I1 dL1 into AR12 by 4 pi R12 square. Okay? So if you observe here, d of df1, so it is related to the first current element in the field 2. Now d of df2 means it is due to the second current element and the field produced is in the first, hence db1. So by default db1 is from the Biot-Savart's law I1 dl1 into AR12 by 4 pi R12 square. So then from this, if you want to find F2, so first if you consider both sides integration one time, then dF2 is to be obtained integral L1, close line integral L1 I2 dL2 into mu naught I1 dL1 into AR12 by 4 pi R12 square. Then to get F2, again we need to apply both sides, or again we need to consider both sides integration. Then consider the square constants are outside. Then mu naught I1 I2 by 4 pi. Then integral, double integral L1 L2, close line integrals L1 L2 dL2 into dL1 into AR12 by 4 pi R12 square. Right? So here if you observe F1, mu naught I1 I2 by 4 pi close line integral L1 L2 dL1 into dL2 into AR21 by R21 square. Similarly, if you observe F2 here, mu naught I1 I2 by 4 pi integral L1 L2 dL2 into dL1 into AR12 by 4 pi R12 square. So the magnitudes and all same, and the directions in which they are moving are different. According to that, AR12 and AR21 are default. Hence, by 2, we can say that F2 equal to minus F1. Means, according to Newton's third law, it obeys as action and reaction are equal and opposite in directions. So, this is the way we have got the force experienced on three current relations as first case. If you observe force experienced on the charged particle, then that is the case First, if you consider electric force Fe as QE and magnetic force Fm as Q into U cross B, then the total force which is related to electric as well as magnetic fields means you combine these two, then Q if you take as common, E plus U cross B. So where Q is said to be a stationary charge, and in the electric fields notation is given by E, and U will be the velocity of an electron and B is applied magnetic field, where this is the equation which is called as Lorentz force equation. It is to be obtained by combining both the force which is considered both related to the electric as well as magnetic force, then magnetic fields, hence F equal to Q into E plus U cross B. Similarly, second one, the force experienced on a current element means in order to derive that we need to recall the relation between three current elements as IDL equal to KDS is equal to JdV. So by recalling all this, consider these two relations, first and last relations. IDL is equal to JdV. Then in place of J, if we substitute according to convection current density, rho V into U into dV, then rho V dV if we replace with the dQ means U into dQ, then IDL is equal to dQ into U. Then according to the magnetic force, Fm is nothing but IDL into B. So, or integral L IDL into B, or differentiation element means dFm is equal to closed line integral L IDL into, right? So this is related to the force experience on a current element. Now, third case we have analyzed just now, that is force between two current elements. Now, to analyze this one, we have to consider two concentric circles which is having the first current, the total entire concentric circle, the current which is flowing through that is I1, and in the current conductor 2, the current is I2. The current element is given by I1 dl1 for the first case and I2 dl2 is for the second case. Now, if you want to find the differentiation element of the force F1 related to the first, or else if you want to find the force related to the second current element as 2, and we want to find the distance from 1 to 2 or else 2 to 1, depending upon that the force which is experienced on the two current elements we have considered as according to the Biot-Savart's law, that is d of df1 equal to I1 dl1 into db2. And the second case, if you consider as for the second field F2, that is d of df2 equal to I2 dl2 into db1. So, any of the two relations which we are going to derive it from the previous two relations, that is df1 is equal to I1 dl1 into db2, or else d of df2 equal to I2 dl2 into db1. So from this, according to this Biot-Savart's law, the relation dH is given by here IDL into AR by 4 pi r square, and we know that the relation between B and H is B equal to mu naught into H. Then differentiation element means dB equal to mu naught into dH. Then if you substitute in place of dH by this equation, then dB is to be obtained as mu naught IDL into AR by 4 pi r square. So instead of considering AR, if you want to find the relation between or distance from 1 to 2, we have to consider it as R12, or if you want to find the distance from 2 to 1, then the relation we have considered it as R21. Now from that, we will be having the final relation F1 is given by mu naught I1 I2 by 4 pi, then closed line integrals L1 L2 dl1 dl2 into AR21 by R21 square is for F1, and similarly for F2 it is mu naught I1 I2 by 4 pi closed line integral L1 L2 then dl2 into dl1 into R12 by 4 pi R12 square. So if you observe this F1 and F2, there must be magnitudes are same and the directions in which they are moving are different. Hence, we have got the relation from F1 and F2 is F2 equal to minus F1. So this is to be obtained from the Newton's third law, that is where actions and reactions are equal and opposite in directions. Right? So this is the way we have analyzed the three cases which are experienced in the magnetic fields. Those are force experienced on charged particle, force experienced on a current element, and the force which is experienced between two current elements. The fundamental laws which we have considered all these cases as Lorentz force equation and Newton's third law, as well as the Biot-Savart's law. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.